Today we're very lucky to have Dr. Shanahan. She obtained her BSc from the University of Adelaide in 2012, and then her PhD also at the University of Adelaide in 2015. She was a postdoc at MIT and then an assistant professor at the College of William and Mary, and simultaneously a senior staff scientist at JLab. She joined MIT as a faculty member in 2018. She has received an NSF Career Award, a DOE Early Career Award, was named as an Emmy Noether Fellow, and was listed in the Forbes 30 Under 30. She is currently the class of 1957 Career Development Assistant Professor of Physics. Today she will be talking to us about proton from quarks to nuclei, the building blocks of the universe. So why don't you go ahead?
Thank you very much, Heather. Okay, it's a delight to be here today virtually. So the topic of this talk is the structure of matter. And of course, we know that matter is composed of atoms, and atoms have a densely packed nuclear core of protons and neutrons surrounded by a cloud of electrons. Our modern understanding is that the structure of matter goes one layer deeper still, so that the protons and neutrons themselves have substructure. They're made of matter particles called quarks, held glued tightly together by the strong force manifesting as force-carrying particles known as gluons. And to the best of our current understanding, this is it. Quarks and gluons are fundamental. There is no deeper layer of structure. Okay, so the quarks and gluons and in their interactions are encoded in what's known as the standard model of elementary particle physics, or the standard model of elementary particles. This framework was put together in the 1970s, and it contains just 17 fundamental particles here. We have 6 matter particles, the quarks, who we've already met. We have the electron and its neutrino and heavier cousins. And then we have force carriers for 3 of the 4 fundamental forces, so notably excluding gravity. We have the photon for electromagnetism, the W and Z bosons for the weak force, and again, the gluon for the strong interactions. And then finally, we have the Higgs boson. So as I said, this theory is beautifully elegant and symmetric and predictive. So as I said, this was written down in the 1970s, but in fact, a number of the standard model particles were predicted before they were even seen experimentally. So most recently, the top quark in 1995, which some will remember, the tau neutrino in 2000, and then the Higgs boson in 2012, which I think many people remember at the Large Hadron Collider, was found as the last remaining piece of this puzzle. Okay, so this standard model is an extraordinarily successful description of the matter in our universe. It's withstood almost every experimental test. And so just to put that in context, an example is the magnetic moment of the electron. This is the most accurately verified prediction in the history of physics. So the magnetic moment it encodes how much torque an electron feels in a magnetic field. What I'm showing here is actually the anomalous magnetic moment. That's the deviation from the tree level or classical result. And what you see here is 12 significant figures of agreement. So for any students in the audience who are studying field theory, you'll have an idea of what a heroic effort this was. It was up to 5 loops of Feynman diagrams. That's about 12,000 Feynman diagrams and 30 years of effort to see this remarkable agreement between theory and experiment. And so just to emphasize this, just a little bit further, there's also remarkable agreement at many different scales. So here's just one more example. This is showing the deep inelastic scattering of an electron on a proton. So that's, we take an electron and fire it at a proton so that the proton breaks apart. This is encoded in what are known as structure functions. And what you see here are these structure functions shown here against an energy scale on a log axis. So you see this scale goes over many orders of magnitude. And you see the predictions in yellow and various experiments in the colored points. And again, you see remarkable agreement at many scales. This is really an extraordinarily successful theory. But of course, we also know that although it is so wonderfully successful, the standard model isn't everything. And so just one example that we'll come back to in sort of the latter part of the talk is dark matter. We know that, in fact, the standard model wonderfully describes the matter we interact with, normal matter, But in fact, most of the matter in the universe is something else entirely. It's dark matter, almost 5 times as much as the regular matter described by the standard model. And this is not described by this theory. And so this is just one example. Dark matter and dark energy. The neutrinos have masses in nature. They don't in the standard model. We know they have masses because we observe neutrino oscillations. So for undergraduates studying quantum mechanics, it's a beautiful example of a 2-state system when the mass and the flavor eigenstate don't match. There's a matter-antimatter asymmetry in the universe we can't explain. So everything is made of matter, right, predominantly. But if the Big Bang created equal amounts of matter and antimatter, where did all the antimatter go if the standard model treats them almost the same? We can ask about, gravity is not included in this framework. You can ask about naturalness. Why is there such a discrepancy between the weak and the gravitational scales? Okay, so this theory is great, but clearly it's not everything. And so one of the key drivers, of course, is to understand and further constrain the physics beyond the standard model. And just one of the ways we can seek to do this, which will be, again, relevant to this talk, is at what we call the intensity frontier. So this is when we are searching for really probing the rarest standard model interactions to search for beyond standard model effects. So this includes things like dark matter direct detection experiments, aspects of neutrino physics, searches for double beta decay, and so on. And the idea is if you're looking for something really rare, you want to increase the probability of seeing it. You want to increase the cross-section as much as possible. So typically you use this, let's take the example of dark matter. You make a very large detector of very many large nuclei, okay, to increase your chances of seeing something. And so if we have experiments searching for physics beyond the standard model that use nuclei as the targets, then we also have to understand the standard model physics of the protons and the nuclei in those targets in order to constrain beyond standard model physics when we see it. So studying the standard model, which is really the topic of this talk, is really important and interesting for 2 reasons. And the first is, in its own right, to understand the emergence of complexity in nature. How do we get from these 17 fundamental particles and this beautifully elegant theory to the periodic table, to chemistry? How does all of that complexity come out from what we know about particle physics? And then secondly, of course, that's tightly coupled to what we need to understand, backgrounds and benchmarks in searches for new physics beyond the standard model. So this really also forms the outline of this talk. Of course, these 2 goals are tightly enmeshed, but we'll go through, after a little bit more introduction, some examples where we're really seeking to understand the structure of protons and nuclei. And then we'll go through some examples of how that can help us constrain backgrounds and benchmarks for new physics. And then finally, I'll come to how advances in computing and algorithms are really driving this first principles understanding of the standard model forward and what we can expect in the future. Okay, so in studying the structure of matter from the standard model, a key and also key complication is the theory of the strong interactions, quantum chromodynamics. So the strong force is, of course, the strongest of the 4 forces in nature. It's what binds the quarks and gluons into protons. It binds the protons and neutrons into nuclei. So if we're interested in the structure of the proton or the structure of nuclei, of course, this is a very important force. It's also responsible for forming other types of exotic matter, like the quark-gluon plasma. But at the low energy scales relevant to, say, the structure of a nucleus at rest, the strong interactions are difficult to study because the interaction strength depends on energy. So what I'm showing here in this figure is the strong coupling as a function of energy here on the horizontal axis. And you see that at low energies, the coupling becomes large. What that means is that we can't do a perturbative expansion in powers of the coupling. Of course, at high energies here, where the coupling's small, you can. So by that I mean 1 power of the coupling is more important than 2, is more important than 3, and you can expand up to some order if you're interested in a result at some precision and then stop. But when the coupling's large, you can't do this perturbative expansion, and theory results are much more difficult to generate. So the only known systematically improvable way of studying QCD, the theory of the strong interactions in this low energy regime, is via a numerical method known as lattice QCD, lattice field theory. And the idea is quite straightforward. You can't do a perturbative expansion. You want to solve this non-perturbatively. You put the equations of QCD onto a space-time grid, a discrete grid, and then you solve them numerically. And what this looks like is these equations end up becoming integrals over the values of the quark and gluon fields on each site and each link of the lattice. So these calculations numerically look like integrals over something like 10 to the 12, 10 to the 9 to 10 to the 12 variables for state-of-the-art calculations. And the way we evaluate them is by importance sampling. So you're trying to do a very high dimensional integral, right? And you can understand this again, just thinking back to a simple quantum mechanics picture, that we of course know that the paths near the classical action dominate and other paths are less important. So you can sample the important paths correspondingly more than the unimportant paths. So you don't waste all your compute cycles sampling the unimportant pieces, right? So this is then how we proceed. To put it in just a little bit more technical detail, because we'll need it later in the talk when we get to algorithms, we're going to a Euclidean space-time grid with some non-zero lattice spacing, some finite box volume, and some calculations even use larger than physical values of the quark masses just because it's computationally cheaper. And as we'll see, these calculations are pushing the limits of computation. So then, of course, to get physical results back, well, you have to take the extrapolation as the lattice spacing becomes small, as the box size becomes big, and as your quark masses become physical, if you took them larger to start with. So the calculations then, we approximate the QCD path integral here, this integral over the quark and gluon field configurations, weighted by the exponential of the action. This is the expectation value of some operator O. We sample the field configurations with this weighting already built in. And then numerically, we end up with just a distribution. We want means and standard deviations over these samples of the background quark and gluon fields will give us our quantities of interest. Okay, so what I want to emphasize here is that the input here into this numerical method is the same three parameters as QCD itself. That is the quark masses and the strong coupling. And you need to fix those somehow to make predictions from the theory, right? So you fix them by matching to some of the measured hadron masses, like the pion mass, the kaon mass, and so on. You need one additional experimental input to fix the lattice spacing, or equivalently the strong coupling. And once you've done that, there is no more input. Everything else that you calculate, all the way from aspects of the structure of the proton to the physics of nuclei, are predictions of the theory. There is no sense in which you're modeling a nucleus as composed of protons and neutrons. Everything else just comes out from QCD itself. So these calculations are computationally extraordinarily expensive. As I hinted at already, we're computation limited. And they use the world's largest supercomputers, many millions of CPU or GPU hours. And just to give you some context, this is Summit here at Oak Ridge. That's currently the fastest supercomputer in the world. And if every person on Earth did one floating point operation a second for a year, that's what Summit can do in 1 second. And we use months of time on Summit. Or to put it another way, some of the calculations I'd show would have taken something like 50,000 years on the laptop I'm using to zoom into this talk. So really large scale computation. But actually it works. So within the last 5 or 6 years, we've entered a precision era for lattice field theory, where for simple quantities, calculations are done with fully controlled uncertainties and uncertainties in some cases better than experimental results. So just a couple of examples. So the ground state hadron spectrum has been reproduced. The proton neutron mass splitting has reproduced. That's what I'm showing here. So here, for example, is the proton neutron mass difference as measured in experiment and is calculated in a lattice QCD and QED calculation. And of course, the experimental measurement is more precise for the proton neutron mass difference. But what the theory calculation gives you, as well as a nice verification, is really, you can see how that small mass difference, of course, so important for the stability of the proton and of nuclei, that small mass difference comes from the competing effects of the strong interaction pushing it one way and electromagnetism pushing it the other way. And through the first principles theory calculations, you can see exactly how that competing effect works to give you the small mass difference we observe in nature. And here are other examples of the mass differences between other members of what we call baryon isospin multiplets shown. And here some of them, the ones highlighted here in blue, are actually more precise than the experimental results. Here's another nice example I like to give from some colleagues. Here are the masses of baryons with a heavy quark. So not just with the light quarks up and down, but with a heavy quark. And the blue data points are all from lattice calculations. The red bars are from experiment. And this particular point here, I added that red bar in afterwards by hand onto the plot. There was a prediction of this state from the lattice calculation, and then LHCb went back, looked there, and found the state exactly where it was predicted. So just one more example.
Sorry, just to interrupt for 1 second.
Go ahead.
There was a question from Nir who was asking a bit for a reminder about QCD. I guess you showed that a few slides back, but perhaps you could flash that again.
Yeah. Yeah, sorry, what was the question exactly?
It was a fairly general one, just a reminder about QCD itself. So I think that's what you're showing on this slide, I assume.
Right, okay, so QCD, or quantum chromodynamics, is the strong force part of the standard model of particle physics. So it describes, so the gluon is the force carrier of the strong force, so it describes the interactions of, say, quarks and gluons and how they are bound to form protons, neutrons, and nuclei. I hope that helps.
Yeah, my question was a bit because that you showed the integral of the QCD, but if it's not important, then never mind. If it is, then, you know, just to know a bit what do we see here.
Yeah, so this was here just showing how you would compute something in field theory from the path integral in QCD. So here we have integral over the gluon fields and the quark fields. The details of this are not completely important. This looks exactly like what you would just write down from field theory, except normally when you're not in Euclidean spacetime, you have an I here with the action, and we're in Euclidean spacetime, so there's no I. The key point I was trying to make here is that we do this integral instead by sampling over these gauge fields according to a known probability distribution. So that's the part of this that we'll come back to. Hopefully that helps.
And then there was another question, sorry, from Giovanni, I think on the slide you were just on. He was asking what the specific output is. Giovanni, maybe you want to say more? Output for the computational operation. I think it was on when you were doing the examples.
Oh, right. So you could calculate, say, matrix elements of how a proton or a nucleus interacts with an external current. So if you calculate the matrix elements of an electromagnetic current in a proton state, that will tell you something about the charge distribution of the proton. Or a matrix elements of a weak current will tell you about how the proton responds to a weak probe, which is what encodes a beta decay rate. So we'll see some examples, but you can compute, you know, matrix elements of local operators that you write down. Yeah. Okay, so just another example of an area where these sorts of calculations have become very important is in flavor physics. So the CKM matrix determines the strength of the weak interactions between quark flavors. So we have here a vertex, a quark of one flavor becoming a quark of another flavor by the interaction with a weak boson here, and that's parameterized by this CKM matrix element here. These parameters are inputs to the standard model. So of course, over-determining them gives you a test on the standard model. And lattice calculations are critical to the extraction of all of these except for VTD. And so there's a real synergy between theory and experiment. So what you can compute, or what you measure in experiment gives you some known factors times the CKM matrix elements times what you can calculate in lattice QCD, which is the relevant hadronic matrix element. So then if you take a very simple experimental process that you expect doesn't have any contributions from beyond standard model physics, you have every piece of this equation, you can deduce the CKM matrix element, then you can go and plug that back in with a lattice calculation of a different hadronic matrix element to make a prediction for something that you expect to be sensitive to beyond standard model physics. So there really is a synergy between theory and experiment here. We had proton-neutron mass difference that you can really understand where that comes from theory. We had theory making predictions for states that are found experimentally. We had the synergy between theory and experiment in the CKM matrix elements, where you need both together to determine those matrix elements. And we'll see this is a continued trend as we go through this talk. Okay, so coming to the first part, the emergence of complex structure in nature. So how does the proton structure emerge from the dynamics of quarks and gluons? So of course, I'll be addressing this from a theory perspective, but of course, as I just mentioned, there's a great synergy between experiment and theory, and finding out how protons, neutrons, nuclei are composed from quarks and gluons is also a defining effort in experiment. So there's a lot of experimental programs targeting the same question. One aspect of this question that my group's been targeting over the last couple of years is the gluon structure of the proton and neutron, collectively called the nucleon. So in some sense, gluons really offer a new window on proton and nuclear structure. Compared to the quark structure, we know far, far less about the gluon structure of the proton or the nucleus. So we do know, of course, that gluons are important in nuclear structure, right? They're the force carriers of the strong force that's binding quarks into protons, that's binding protons into nuclei, but also aspects that we've been able to measure the gluon's importance. So here's just one example. Here I'm showing the Proton distribution functions in the proton. So this F here is the number density of quarks or gluons of some type of flavor F. And X here is the longitudinal momentum fraction carried by that quark or gluon. So this plot is against that longitudinal momentum fraction. So you see these distributions here for up and down quarks, for strange and other C quarks, and the gluon. And you see that the gluon is really dominant at these low longitudinal momentum fraction days. So of course, the gluon's important. But compared to everything we know about quark structure, including spin-dependent aspects, we know far, far less about the gluons. Essentially, they're just very difficult to measure experimentally because of course, the gluon doesn't couple to an electromagnetic probe. And so there's a lot of experiments in the next decade looking to understand aspects of the gluon structure of the proton and nuclei better. So to give you an idea of what I mean, aspects of the gluon structure, we won't get to talk about very many of these today just because of time, but I mean, from the simple static questions, how much do gluons contribute to the momentum, to the spin, to the mass, to something called the D term of the proton, through the sort of more three-dimensional questions, which are encoded in things like Proton distribution functions that we just saw and form factors. So what's the role of the gluon in the pressure distribution of the proton, in the three-dimensional distributions? And then, well, but what about in nuclei? How's the gluon structure of a nucleus different from the gluon structure of just protons and neutrons? How's the nuclear binding from the strong force show up? And so these are all questions that we can seek to answer, and we're working on aspects of all of these from first principles calculations. So just a couple of examples. So here's an example of a highlight in 2020 of the decomposition of the proton momentum. So this is an example of a calculation where everything is completely systematically controlled with uncertainties competitive or better than experiment for some quantities. Something that you can do easily in theory calculations that's harder in experiment is to separate out contributions from different quarks and from gluons all very cleanly. So here's an example of all terms of the momentum decomposition of the proton. So this is what fraction of the proton momentum is carried by up quarks, down quarks, strange quarks, charms quarks, the gluons, and it all adds up to 1, as of course it should. Between them, they all carry 100% of the momentum of the proton. So we can go to something a little bit more dynamical, a bit more 3D, and ask about the pressure distribution inside the proton. So of course the proton's stable. So if we have some sort of repulsive pressure, some expanding force, then there must also be some compensating confining pressure, some compressive force for stability. So a cartoon of the pressure distribution in the proton, so moving out from the center of the proton here along a radial distance, could be something like this. On this vertical axis, I have that radial distance squared times the pressure. I'm showing this particular combination because this is what has to integrate to 0 for stability. So you might think that there's a repulsive pressure near the center of the proton, and then that would have to be compensated by a confining pressure as you move out further along a radius. But then there's a lot of questions, right? How do quarks and gluons contribute to the pressure in the proton? What's the peak pressure? Is the pressure in a proton more like a bike tire at 10 to the 5 Pascal, or more like a neutron star at 10 to the 34 Pascal? What's the radial extent? How far out from the center of the proton does the pressure distribution go? And so these are some questions that we've addressed in the last couple of years by combining theory and experiment. So there was some nice experimental work extracting the proton's pressure distribution for the first time. And what was found is that the peak pressure near the center is actually an order of magnitude greater than that estimated in the interior of neutron stars, so the densest known object in the universe. But the experiment, which was via deeply virtual Compton scattering, was only sensitive to the quarks, not the gluons. So what we were able to do was actually compute the gluon piece of the pressure distribution, combine it with the quark piece from experiment, and together have the first complete pressure distribution of the proton. And of course, this also lets us explore what kinematics you would need in future experiments to measure this piece that's never been measured. And what we see is that gluons actually change the picture. So this is the same figure as the cartoon. This is the radial distance squared times the pressure, and here's the radius. The blue, the dark blue here, is what you get if you consider only quarks. So from the experimental result. The red here is what you get if you include gluons. So you have a higher peak, you have slightly shifted peaks, and you also have a greater radial extent of the pressure distribution when you include gluons. So by combining theory and experiment, we can really understand some of these fundamental aspects of proton structure for the first time. We can also sort of expand on that. Well, look at pressure distributions of different hadrons, not just the nucleon, but how does it compare to the pion? And you can think of this as really giving you an extra dimension on this structure. So if you look at just the momentum fraction, how much of the momentum is carried by quarks and gluons in the proton and in the pion? It's about 50-50 in each case. It's very similar. But if we go to this extra dimension, if we go to say a pressure distribution, you have here quark in purple, gluon in green. You see that from the nucleon to the pion, there's quite some difference. Here the peak is dominated by quarks, here by gluons. In both cases, the gluons seem to push the radial extent out from just a pressure distribution from the quarks. And so we can really begin, this is the first results, we can really begin to understand hadron structure in a new way. A natural question is to say, well, if we can look at the pressure in protons and neutrons, well, what about nuclei? And this is something we're working on now too. And then eventually you might imagine that if you look at neutron-rich nuclei, maybe this could help give you some insight into the equations of state of neutron stars, sort of in a far future application. So this is something we're working on. And the reason these results aren't here yet is that this is very hard. So just to give you some context, nuclear physics from lattice QCD is hard computationally. So you're facing compounding exponentials and factorials. So essentially the noise, remember we're doing these calculations by sampling, grows exponentially with the quantum numbers of protons and neutrons, with the number of protons and neutrons, but also the cost of doing each calculation for each sample grows factorially. So you have compounding exponentials and factorials, and calculations are only possible for light nuclei at the current time, purely computational limitation. So we've been pursuing this for a number of years, as have a number of other collaborations, I should mention, including some locals, the Cal-Lat collaboration with Andre Walker-Loud and collaborators, to try to do nuclear physics from lattice QCD. Sort of the first calculation of the spectrum of light nuclei was in 2013. Some exciting results from recent years that I won't get to talk about. I'm just flashing here. We've looked at things like proton-proton fusion, tritium beta decay, double beta decay, the gluon structure of light nuclei that I hinted at. But today we'll get to these highlighted topics. So one of the simplest aspects of trying to understand how the structure of a nucleus is different from that of protons and neutrons is to ask about some of the quantities we've already seen, like the momentum fraction. So these types of effects, these types of nuclear effects, are what we call EMC type effects, named after the European muon collaboration, who first saw these sorts of effects in 1983. So they did deep inelastic scattering, which we talked about at the start, and they saw that deep inelastic scattering off a nucleus is not just the sum of deep inelastic scattering off the individual protons and neutrons, that there is nuclear effect there. And so this is the deep inelastic scattering cross-section ratio per nucleon for iron to deuterium versus the longitudinal momentum fraction here. And you see that this is not one, right? Nuclear effect in this quantity. We can look for nuclear effects in various quantities, and one of the simplest is in the momentum fraction that we saw before for the proton. So what I'm showing here is the ratio of the momentum fractions in helium-3 to that in the proton. And on this axis is the up minus down quark combination, and on this axis is the up plus down quark combination. So how much momentum these combinations of quarks carry in helium-3 divided by the same in the proton. So from fits to experimental data, you have this blue ellipse here. Then from our first principles calculations, we're able to put this red band on the plot. So even though the calculations we did were at larger than physical values of the quark masses, and we have to extrapolate them to the physical point by matching to the low energy constants of effective field theory and then extrapolating, which inflates the error bars, we still have a tighter constraint than experiment. We can include that back in to the global fits to experimental data to get this purple ellipse, and so improve our constraints on this aspect of the structure of helium-3. And even though the input from the lattice QCD calculations here was just this one number, the ratio of the up minus down quark combination of momentum in helium to that in the proton, adding that constraint into fits to experimental data actually improves the parton distributions that we saw before, these number densities of quarks of some flavor. This is the ratio of these parton distribution functions in the helium-3 to the proton versus the longitudinal momentum fraction x. And you see an improvement from the light blue to the purple by including just that one number from the lattice QCD calculation. So here we're seeing nuclear effects really from the quarks and gluons of the standard model. We're understanding them from first principles, and we're able to add that knowledge into fits to experimental data to better understand the structure of nuclei. So understanding the structure of nuclei, as I hinted earlier, is of course also important when we're searching for physics beyond the standard model. And I'll give just one example in the context of dark matter. Of course, there is compelling evidence for dark matter, right? Just some examples. I mean, this is a picture of the Coma cluster, a large cluster of galaxies near Earth, where Fritz Zwicky in the 1930s saw that the gravitational mass needed to hold that galaxy cluster together was more than what you can infer from the luminous matter from the stars. It shouldn't stay together. We have evidence from rotation curves. We have pictures like this of the famous bullet cluster and many other clusters where what you have here is in false color pink, where the mass is from the luminous matter that you can see, and in purple here, where you can infer the mass is through gravitational lensing, and you see they're not the same. And you can understand this as having galaxies collide, and the normal matter collides and sort of stays in the middle, and the dark matter continues on, and you get this separation. So there's really a long list of evidence for dark matter. And as we sort of hinted at the start, our picture is that normal matter that the standard model describes is only this 5% of the energy density pi, and dark matter that doesn't emit or absorb light, that's why it's called dark, but we know it's there through gravity, is 5 times that. And the rest is dark energy, which we don't understand, but we know something is responsible for the accelerating expansion of the universe, and we call it dark energy. Okay, so there are many models for dark matter, but in some sense, few constraints. And in this context, I like to show this figure from Tim Tate that sort of tries to summarize a variety of the models for dark matter. We have supersymmetry, extra dimensions, we have sterile neutrinos, we have dark photons, Higgs, axion-like particles. There's a big theory space, right? And what we need to do is rule out or support different theories in this space in order to understand what dark matter could be. So one way of constraining dark matter, and of course there are others, is through direct detection experiments, where we look through terrestrial experiments for evidence of dark matter interacting with our detector. So this might happen if you have a WIMP dark matter candidate, or a weakly interacting massive particle candidate for dark matter. And sort of very loosely, the way direct detection experiments work is that you bury a big vat of nuclei deep underground to shield it, and then you wait to see some effects of dark matter interactions. And of course, the detection rate depends on the properties of the dark matter, which is what we want to constrain, but also the probability for the interaction with the nucleus, right? So you might have seen figures like this. These are limits on the interactions of these weakly interacting massive particles with nucleons, protons or neutrons, from these direct detection experiments. So on this axis, we have the mass of the weakly interactive massive particle. And on this axis, the interaction cross-section for this particle with protons or neutrons. And all of these lines are from experiments. And the way to read this is that all of the space above the lines is ruled out, right? But something to notice is that this is the WIMP nucleon, that's proton or neutron cross-section. But the experiments are not done with protons or neutrons. For example, this one's done with xenon. That's a very large nucleus. There's 130, 140 protons and neutrons in it. So somehow in making this plot, this exclusion plot, what's happened is a translation from not seeing dark matter interacting with xenon to a constraint on the properties of the proton, dark matter interactions with the proton. So the simplest way to do this is to assume a Born approximation. That is that the dark matter interacts with a single proton or neutron in the nucleus at once, right? Then the interaction cross-section is just the cross-section for interaction with a proton or neutron scaled up by the number of protons and neutrons, right? And this here, the interaction of dark matter with a proton, is something we can calculate very precisely from lattice field theory, right? We're in the precision era for these sorts of calculations for whatever your model of dark matter is. But what if it interacts non-trivially with multiple nucleons? What if you have a two-body interaction like this? Well, this is not known. And the second term could be significant, and that would change the limits you draw on that figure from not seeing the interaction of dark matter with xenon to the constraints you say you have on the interaction of dark matter with a proton or neutron. So at the very first efforts to try to address this issue, we studied the scalar matrix elements in light nuclei. So although we don't know the microscopic theory of WIMPs, weakly interacting dark matter candidates, the low energy limit of a generic spin independent interaction is scalar. So the relevant coupling is the scalar matrix elements. And so we did a calculation for the deuteron diproton, which is stable at this quark mass, and helium-3. And what we saw is 10% nuclear effect. So the way to read this plot is that 0 here is just the Born approximation, no nuclear effects. And deviations from 0 are nuclear effects. And each different column here is a different combination of quarks. So here is up minus down, up plus, down plus strange, and so on. And what you see here is for helium-3, we have something like 10% nuclear effects. To put this in context, for the axial matrix elements, which we can measure in nuclei of various sizes, in helium-3, you have a fraction of a percent nuclear effects in these calculations. But in medium mass nuclei, 40, 50, 100 protons and neutrons, you have 20% nuclear effects, whereas it's only a fraction of a percent at this scale. So we're seeing 10% nuclear effects in helium-3. And then what you really want to know is the nuclear effects in, say, xenon, which we can't constrain from these calculations, but you want to extrapolate up. And so what we can say is that these really unexpectedly large multi-body effects can't be neglected in the interpretation of dark matter direct detection experiments. So, of course, these calculations have as yet uncontrolled systematics. I said the pion mass is larger than it is in nature. We're doing calculations at close to the physical quark masses, and we're going to try to go to larger nuclei as well. And so stay tuned. So getting to larger nuclei, well, really the way to do it is via nuclear effective theory. So I said we had unexpectedly large two-body effects that were 10%, right? We still do have a hierarchy. One body effects are dominant, two body effects are sub-leading but non-negligible. So you can think about determining the one body contributions from single nucleon, few body contributions from 2, 3, 4 body calculations, matched to effective field theory and many body methods to make predictions for larger nuclei. And there's also locals working in this direction. So to come to just the last bit of the talk, well, what if we start asking, will we ever be able to get first principles nuclear physics beyond A=4? And of course we'd like to, right? Dark matter direct detection is just one example. The June long baseline neutrino experiment that's looking to measure the neutrino mass hierarchy and oscillation parameters, that's doing neutrino scattering on argon. What you'd really like to know is the axial form factors of argon and how much they differ from just multiplying up those of the proton. Double beta decay experiments looking to see if the neutrino is its own antiparticle or not. The lightest nucleus that undergoes double beta decay is calcium, A=48. We'd love to be able to calculate decay rates there. Like I said, scalar matrix elements, we'd like to know them in xenon, not in helium. So what's stopping us is really, these are exponentially harder problems. So if we want to have any hope, we need exponentially improved algorithms. And so that brings us to this last part of the talk, is how advances in computing and algorithms are, advancing what we can do in this area. And I want to give you just one example. So one of the computational steps you have to do in these calculations is generating the field configurations. That's why I showed that integral at the start of the talk. Just mathematically, we need to generate field configurations here with this known probability distribution given by the exponential of the action, right? So what we usually do is a procedure known as hybrid Monte Carlo or Hamiltonian Monte Carlo. You're doing a coupled position and momentum walk through Hamiltonian dynamics to explore this space. And it works via a chain. You make some small update to your configuration in a chain. You have some burn-in time, and then you have some correlated steps, right? You're making small updates, so your steps are correlated. And then the cost to sample has something to do with the correlation length here, because you want to sample independent configurations. And one of the challenges with this method comes that these updates are in some sense diffusive or close to local. So they step outwards in lattice sites, right? So what that means is if you want to update physics on a fixed physical length scale, like the size of a proton, well, if you have a coarse lattice spacing, maybe you update your configuration on that scale in just a few steps. If you have a finer lattice spacing, and of course that's a limit we have to take as we go to the continuum limit to match to physics, you have to do more and more updates to change physics on that length scale and get uncorrelated configurations. And this is critical slowing down. And especially as we go to larger states, heavier masses, we want finer lattice spacings, this becomes a serious problem. And this is a problem that my group's trying to address through new algorithms. So just to state the problem again, we want to sample field configurations from a known probability distribution. So if we think of the field configurations like this is actually what they might look like for a scalar field theory, where you have just a real number on each site. We want configurations that look like this and not like this. This is just random noise. You can see it has different correlation structure. This is very unlikely. These are more likely. This looks a lot like problems that we've seen the machine learning community tackle in the last few years. A lot like, has very many parallels with the image generation problem. So these are not photos of people. These are machine generated images. You can go to thispersondoesnotexist.com, and every time you refresh, it will give you a new machine generated image that looks like someone's face. And so people have managed to train machine learning algorithms that will give them pictures like this and not this, which is a lot like our problem. We want things that look like this and not like this, with one very important difference. They never want this, right? We do actually want this to happen with a very specific probability. Okay, so one of the key differences. So the way we've been addressing this sampling problem is really drawing inspiration from what's been done in machine learning, but reinventing it from the ground up for our problem. So one approach is to use what are called flow-based models, and the idea is very simple. If you have a change of variables that takes you from an easy to sample distribution to the complex distribution that you want, well, then you're done. You can just sample from the easy distribution, put it through your function, and out pop samples of the complex distribution that you like. So flow-based models let us actually keep track of the densities, and so we end up having a way of being able to make this exact, even if the model is not exact, through accept reject steps. So we have a way that if we can learn this change of variables, we have an exact sampling procedure. So we can generate functions like this by composing them from many simple functions in a way that we still have an invertible function with a tractable Jacobian that lets us do this. And then we can optimize the parameters of this function to let us sample from the distribution of interest. So I just want to emphasize a little bit the ways in which this is different and the complications we face in trying to do this that are different from applications in industry, say to image recognition. So one of them is that physics is invariant under very specific field transformations that images typically aren't invariant under. So for example, rotations and translations in 4 dimensions with boundary conditions. If this is a field configuration, a rotated translated configuration with periodic boundary conditions is the same thing. It encodes the same physics. Similarly, we have gauge transformations. So exact definition here, but that's really updating each link on the lattice in a different but correlated way. And again, physics is invariant under this complicated transformation. Again, a symmetry that images, of course, don't have. So if we compare an ensemble of lattice gauge fields to a benchmark image set for machine learning, we see some very significant differences that make this challenging. Firstly, each sample of ours is described by something like 10 to the 9 to 10 to the 12 numbers, and we'd like, 1,000, a few thousand samples. So each sample has way more degrees of freedom than the number of samples. Benchmark image set, each sample is described by 3,000 numbers, and they use 60,000 for training. Clearly, the same sorts of training ideas aren't going to work for us. It's really the ensemble of gauge fields that has meaning. We want a precise probability distribution over them instead of each image having meaning in itself. Long distance correlations are important for us, whereas in an image you have local structures like a nose or an eye that are meaningful in themselves. We have these complicated symmetries that you don't have in images. Okay, so we can be inspired by what's done in machine learning, but we really have to go back and design algorithms from the start. So in our gauge field theory, this field configuration that we're sampling is represented here by links, which are encoded as matrices. So for QCD, we have 3x3 complex matrices with unit determinant. The very first thing you face is that, well, group valued fields don't live on the real line. It's a compact connected manifold. So first you have to design flows on compact connected manifolds, even just a circle, an angle on a circle. How do you do machine learning on that without having a discontinuity at 2 pi? So we had to go back and design this. Then how do you incorporate symmetries like gauge equivariance? And so I won't tell you too much about the technical details. They get quite heavy, but I'll show you a nice picture that gives the general idea that we designed new structures that incorporate these correlated symmetries between nearby group elements in each layer of our flow model to design gauge equivariant flows that are equivariant under these symmetry transformations, so we can create actually invariant models. And we had to go back and first start with compact connected manifolds, but then build in gauge symmetry. And it turns out that in doing this, you can actually succeed in this challenge. So here's an example of an application to a U1 field theory. QCD is SU3, so this is a little bit simpler. And what we found is that we really significantly reduced or eliminated this critical slowing down problem at the cost of the upfront training of the model. So what I'm showing here is the sampling of the topological charge. So this is, it's the winding number of the gauge field. So the ITSing index theorem tells us that it's quantized. It's a global variable integral over all of the sites. And what you're seeing here is this topological quantity as a function of the step in one of these updating chains. And this line here is hybrid Monte Carlo or Hamiltonian Monte Carlo, so a conventional approach. And you see it gets really stuck in one topological sector for a very long time. We have a frozen topology. It's not sampling the field configurations efficiently. In black here, we have a heat bath approach. That's another conventional approach. It does a bit better, but it's still not sampling these different sectors very efficiently at all. And then the orange is the sampling from our machine learn model. So it doesn't get frozen because the samples are drawn independently. If we ask what this means for cost per independent sample, it's what I'm showing here. This is a measure of the autocorrelation time, or a measure of cost, essentially. And on a log axis, you see Hamiltonian Monte Carlo, hybrid Monte Carlo, heat bath. The conventional approaches are diverging exponentially badly along this critical line as the lattice spacing becomes small. And our flow approach is almost flat. So it's orders of magnitude better than the conventional approaches. So this is a great success. But it really is at this stage a proof of principle of a very efficient, exact machine learning algorithm for lattice gauge theory. I showed you results in U1. We've already extended to SUN for QCD, but there's still significant work needed to scale this to the state of the art. So we're working to scale for Aurora, which will be the new largest supercomputer in the world to be built at Argonne in the next couple of years. We have early science time there. And the goal is to run some of the largest machine learning models that have been run on that supercomputer for this task. But just before I finish, we're still scaling up to our target application, but actually these tools are already useful for other applications. So the same ideas have been applied to molecular genetics and drug design, where they're already at a scale to make significant impact. Actually, even the same ideas have now been applied to robotics, because of course, if you think about the joints of a robot arm, they're described by angles, which live on compact manifolds. And so the techniques we developed for compact manifolds also have applications there. Okay, so this is the summary. I talked about nuclear physics from the standard model and how that can give us new insights into proton and nuclear structure, both to reveal nuclear structure for its own sake, but also for benchmarks and backgrounds for searches for beyond standard model physics. And then how, since we're computation limited, new algorithms and machine learning can help us break those computational barriers and do more exciting physics. Thank you very much.
Great, thank you. You got to imagine that we're all clapping. I'll do some job of it.
Thanks, Heather.
Thanks a lot. And let's see what questions we have. I see there's one from Sherwood. Do you want to go ahead?
Phiala, that was a really wonderful talk. Thank you so much.
Thanks, Sherwood.
I have a basic question from all the way back in one of your first slides. There was I forget which number it was that you were comparing the result from experiment and from QCD. And they were accurate to, what was it, 14 digits?
Yeah, that was for the, I don't know if you can see, I have a spinny wheel, but.
Okay, no, I can't see it, but.
My slide just
so
stuck.
there were discrepancies down.
Magnetic moment.
Okay. Yeah, but there were discrepancies down past those 14 digits and that seem to be larger than the uncertainties. Is that indication of new physics or some unexplained systematic error?
Oh, I didn't notice that they're larger than the uncertainties, actually. There's not a sign of new physics, for sure. Okay. I don't think anyone's expecting new physics in the magnetic moment of the electron. No, I think they're consistent within, a couple of standard deviations, certainly not 5 standard deviations discrepancy.
Okay. So the parentheses just indicate 1 standard deviation.
Yeah, that's right.
All right, that's it. Thanks.
No problem.
Great. Thanks, Sherwood. I see Sunwon. Are you able, do you want to unmute and ask or type your question?
Hi. Hi, Phiala. This is Sunwon. Good to see you here, and thank you for the nice talk. Can you hear me?
Yes, I can hear you.
Great. So I have a question regarding the machine learning part.
Yeah. So
actually 2 questions. The first one is, the way I understood is that you do the machine learning in order to do effectively some new parameterizations or the variable change. so that you are sampling from in the parameter space, which looks more convenient or like easy to sample.
That's right.
If that's the case, I would say what the machine has learned might contain already a lot of useful information about the structure. So maybe it'll be used like directly rather than to use it as an efficient sampler. And then I wonder if you have any comments on that.
Yeah, I mean, so we do know what sort of a transformation would take you back to a trivial distribution. Martin Lucia wrote down trivializing maps, which do exactly this. So essentially, we're trying to machine learn a computationally feasible approximation to that.
Yeah, that's right. So can you look into the details of this transformation and actually learn about the structure from the transformation?
Yeah, so you can try to do that. We haven't learned anything deep by trying to do that, to be honest. And it really depends also on the architecture that you're making. So there are ways of trying to make this more physical. So one thing that you could do, for example, is make this easily sampled distribution, something like a free field theory. And you could even step your flow specifically along and train intermediate layers to correspond to different coupling strengths. So you can try to guide it along some particular physics trajectory so that you can understand better. We've typically found that allowing it to go up into sort of higher dimensions away from such a constrained directory does better in the end, but that also makes it less interpretable.
I see. My second question is actually related to your last comment. So does this machine learning trained method works better than by hand doing certain well-known transformation by well-known approximation?
Yes, there's no other way of doing this sort of a sampling efficiently that I know of.
I see. Mm-hmm. Thank you very much. Yeah.
No problem.
All right. I see a question in the chat from Giovanni. He wants to ask, is QCD an ever-expanding discipline in physics and academia? This question might sound obvious, although I would like to know any potential applications for the whole of physics.
Yeah, well, I mean, QCD is the theory of the strong interactions, the best one that we have. So as far as ever expanding, I'd say that it's really only recently, so since I was a graduate student, that we've reached a precision era in that you can really think of doing first principles QCD calculations with controlled uncertainties such that you might, compete with experiment or input into experiment or compare with the experiment to find new physics. So that's really a new and growing phenomenon. And especially going to nuclei where, we're not yet at the stage of controlled calculation of nuclei, but we're right at the edges. So that's also going to grow. The world of first principles QCD input into nuclear physics is only just beginning.
Great. And I think, Sherwood, maybe you have a second question.
Nobody else has questions. Yeah, so you talked earlier about you showed a plot that showed that the multi-body effects are non-negligible. But that was a calculation that was done with wrong quark masses, right? And you said that you're actively working on realistic quark masses. But if you go the other direction and the masses get more wrong, is that inconsistency a robust feature? Does it grow or shrink as the masses diverge from reality?
So we haven't made the masses larger to look. We have calculations with masses about half as wrong, and it seems to be consistent. And we have very preliminary results on calculations very close to the physical point. And within the uncertainties, it all looks pretty consistent. But the uncertainties are large. So,
okay.
I mean.
All right, thanks.
And I think we'll take one last question. So it's from Sam. Sam wants to ask, is the state-of-the-art QCD at the point where you could replace the cartoon picture of nuclei of spheres stuck together that we learned in school with a more accurate picture?
So that's exactly what we're trying to do in studying these nuclear effects from first principles. So I gave just a couple of examples of the scalar matrix elements, so relevant to dark matter, and of the momentum fraction, which relates to the Proton distribution functions. We've also done some interesting work on the gluon distribution in nuclei, which I think is the closest to wanting to replace the cartoon picture. And one of the quantities you can calculate is a double helicity flip gluon distribution. So what that means is just that through this interaction, if you have a positive helicity target and a negative helicity photon, they both flip. What that means is that the proton can't do that because it has spin half. So this particular structure function, it vanishes in a proton at rest, but it doesn't necessarily vanish in a nucleon of spin 1 or larger at rest. And it also happens to be purely gluonic with no mixing to quark distributions. So all that to say is that you can calculate a quantity which vanishes in protons and neutrons, but doesn't vanish in the nucleus and is gluonic. And we found that this is non-zero, which hasn't been measured experimentally yet. But what this really tells you is that you do have, gluonic interactions, strong force interactions between, multiple nucleons in the nucleus. So if you want your cartoon picture of protons and neutrons stuck together, I mean, the protons and neutrons still are pretty good degrees of freedom. That model works really well, but you might want to add some extra curly gluon lines to them and sort of distort them slightly.
All right. I guess that's the end of our questions, unless there are any more. Okay, well, thanks again. Thanks for joining us and giving us this excellent talk. And thank you, everyone.